Hello. I'm happy to present our work on fair and adventurous enumeration of quantifier instantiations. My name is Mikola Janota, and this is joint work with Aniel Barbosa, Pascal Fontaine, and Andrew Reynolds. And before I go into the name of the paper, let me say a few words about how quantifiers are dealt with in satisfiability modulo theories. So let us consider this simple formula that says that f of x is always at least x, but at the same time, f of y can be at most 5. Now, this is obviously a contradiction, and how do we show that? We instantiate each of the variables by the value 6, for instance. So this gives us a contradiction that says that f of 6 must be at least 6, and on the other hand, it is at most 5. And then this is easy for the ground solver to refute. So the tricky part is how to come up with the right instantiations. There is a theoretical background to this, which we call the Herbrun Theorem, which tells us that if I have a first order logic formula that is unsatisfiable, I can ground it. I can instantiate the quantifiers in a way that makes it unsatisfiable. And it's sufficient to consider only the terms from the Herbrun universe, which is essentially just the terms that I can build from looking at the symbols in the formula. So for instance, if I have this formula that contains f and a constant c, then the Herbrun universe is an arbitrary number of compositions of f applied to c. So the universe is infinite, but we have a bit of a handle on it. There is an improved or an extended version of the Herbrun theorem that is used in SMT, and that is that we only need to look at the terms that are in the formula. Now, what do I mean in the formula? So let's say I have some formula for all x and phi. So this is quantified, and g is something that a user wrote that is not quantified, so it's ground. So I can pick any term from G. So I'm relying on the terms that are only written by the user. And I get a new instantiation, which have grown the ground part. So now we actually have a bigger pool of terms to look at. So this ground part obtained by instantiating the quantified formula gives us a bigger pool, and this continues on and on. Okay, so this is a good way of looking at it because now we have a finite number of terms in each step to look at, even though eventually we may generate an infinite number of terms in the process. Of course, in theories, things get much more complicated, so this is not complete. So consider, for instance, this very silly example where I'm saying that c is equal to 21, and I'm saying that there is no way of multiplying two numbers that get me c, which is of course not true, and it's sufficient to instantiate with 3 and 7, for instance, but there is no 3 and 7 nowhere to be found in the formula. Okay, but anyhow, we rely on Herbrun because the problem is inherently extremely difficult. So what we do is we look at the terms that we have currently in the formula, we instantiate and call the ground solver to check if it's unsatisfiable, and we repeat. However, what is the good order of instantiating terms? So what are the good terms to pick from? So the pool of terms is growing and growing, and the question is, what is a good order? And from practice, we have observed that terms are like wine, meaning that all terms are good. So again, if I have the ground part and quantified part, and I get this kind of an onion structure where the terms are growing and growing, it's better to start with the older one and move to the newer ones afterwards. So the order we are getting is that first we get instantiations by terms coming from the user, then the instantiations that we got in the second level of the group of the onion, and so on. Okay. So this is fairly clear, and this has shown to be working well in practice. But the question is, what about tuples of quantified variables? So let's say I have 3 variables, x1, x2, x3, that are quantified over, and I wrote down the order here in each of the columns. So this is the age ranking, right? So the first is the oldest one, but we're asking, what is the good order for tuples? And this is the main focus of this little work that we have done here. And the best idea to start with is that we pick the best term for each of the variables. And that is easy. So the first tuple is easy to pick. I pick the best best terms for each of the variables. Now I can go and pick as the next tuple something that worsens this only a little bit. So let's say I worsen the third variable, and then what next, right? So I can, for instance, worsen the second variable, but you might say, well, you should have actually gone back with the third one and try all the options. However, I'm neglecting the first variable. So that is not moving. So if I have many variables, I might be trying many options without changing the first one. So this is being unfair to the first variable. So the question is, how do we go about this conceptually? And we came up with this kind of a lattice where we see how we can gradually worsen the tuples. So the first one is the best one. So the rank is 0, 0, 0. And then I can decide that I worsen the rightmost variable, the middle variable, the left variable, and so on. And I kind of repeat this recursively, and I'm getting this kind of a lattice style graph that tells me how I can minimally worsen each of the configurations. Now, this is what gave the title to the paper, that if I go deeper into this graph, I'm being more adventurous because I'm trying more new things. And however, if I'm more broad, I'm being more fair to the variables because I'm not worsening one variable on behalf of another one. So let me say a few words about the different strategies that we have came up with that let us traverse this tree. And the first one is maximal digits, where we go in stages and we enumerate all numbers in a base B, where base B is being increased. So first one, we start with 0, so there's only one combination. Then we go all binary, so we let the maximal digit be 1. Then we go all base 3, so maximal digit is 2, and so on. Okay, so this lets us do this in stages. Now within the stage, we break ties by just doing lexicographic. The disadvantage is that we might change a variable late, because as we're trying the combinations, the most significant digits tend to change late. Another approach is that we increase the sum of all the digits. So first, in the first stage, the sum is 0. In the second stage, the sum is 1, and the sum is 2, and so on. This is essentially breadth first search in our lattice, and it's quite fair. Another approach comes from economics. It's called leximax, and the idea is that we worsen as little as possible and then do all permutations of this worsening in order to maintain this fair. Okay, so we start again with the best combinations, and then we worsen one of the variables and then do permutations. Then I worsen two variables and do permutations. And now I worsen one variable by two and do permutations. Then I worsen all the variables, and there's just one permutation because all are equal. And so on. For a more precise definition, you can check the paper. And finally, for a more adventurous strategy, we have the random walk, which essentially just goes in a random node as long as its parent is already explored. So this can have different shape, and this is more adventurous strategy, whereas the others were tending to be more fair. All right, so let me say a few words about the experiments. So we have compared the enumerative strategies in CVC5, and we also compared to e-matching. So here the first column is e-matching, which wins on all the families tried, except for Ufnia, where somehow the enumerative are much better. We don't have a good explanation for why. And the max digit is winning, but maybe not by so much. We also compared it to Z3, and we did a portfolio, so virtual best solver of the enumerative approaches. And here we can see that this really gives us some additional instances solved, some edge, that they are somewhat complementary. So this improves the robustness of the solver. So now the difference between e-matching and the portfolio is much smaller, even though there it's still notable, and it has improved significantly over the best strategy in the Ufnia family, where it was already very good. Okay, so just to conclude, what is the goal of the paper? We have order on a variable. So this is the age, let's say, it could be a different one. And we're asking what's the order on tuples. And we define a number of strategies that we have implemented in CVC5, and that has diversified the solver. And we're based on this kind of a Pareto ordering, meaning that we try to worsen things as little as possible. And the question is, could we somehow learn when each of the strategies is better, right? So we saw that the virtual best solver diversifies the initial solver, but we don't know when to pick one of the strategies. And also all this work kind of assumes that the strategies on variables can be independent of one variable from another. And the question is, can we do something that actually looks at a tuple as a whole? So consider some sort of dependencies between variables. Okay, so that is all from me, and I'm happy to take questions at the conference.